It's my pleasure to invite Untitled Chapter, who is a faculty member here in Atmospheric and Oceanic Sciences, and has been working, and it's a lovely, given that we have the warmest day of the year, probably a nice day to think about tropical weather, since it probably feels tropical at some level today. I would be disappointed if I don't see somebody grilling in shorts outside this afternoon. But moving on to here, Angel got his bachelor's degree in physics at the University of Puerto Rico, Mayagüez, and then got a master's and PhD at the University of Washington in atmospheric sciences. Before joining our faculty here, he was a postdoc at NOAA GFDL in Princeton, as well as faculty at the University of Michigan. He's a Kavli Fellow at the National Academy of Sciences, and in 2018 he was an awardee of the James Holton Award for the American Geophysical Union, which is a very high honor from that society. So Angel's going to talk to us today about some of his work in thinking about tropical weather and climate, and the title of the talk here is What Do Weak Temperature Gradients and Moisture Modes Teach Us About Tropical Weather and Climate? So please teach us, Professor Adiabatic.
What a great pleasure, and good afternoon, everybody. I am very surprised to see such a full house right now. I feel like the stakes are quite high. I see that John and Michael are back in the front. We got everybody here looking. We got my students from both my research students and my 611 students here. So, I feel like we got the whole shebang going on in here. So it is my great pleasure, like I said, to be talking to all of you today. And what we're going to be talking about is the weak temperature gradients and moisture modes. If you don't know what that is, I will define it today. And what we learn about weather and climate. I actually have a QR code here. You see it there at the beginning. I'm going to put it at the end. That gives you the URL for one of the papers that I'm going to be discussing today, which is currently revised and hopefully will be accepted soon. All right. So I always like to start off my talks by showing people that the tropics and the subtropics are actually like a really big chunk of our planet. So here is like think of Himawari on the right and then a GOES 16 on the left. Satellite image of infrared brightness, infrared temperatures, and you can see, actually the tropics, 30 degrees north and south of the equator, roughly, it's like actually about half the size of the planet, half the area of the planet. So it's really important to think about tropical weather and climate because it is actually half of the globe. So with that said, okay, Angel is studying, stuff that happens in the equatorward part, equatorward half of the planet. Why does this matter? So it turns out that the tropics, all these countries are, here's the Tropic of Cancer, here's the Tropic of Capricorn, the equator. A lot of countries are located in the tropical belt defined within the Tropics of Cancer and Capricorn. In fact, over 40% of the global population lives within these two tropics. And actually it goes to over 50% if you go up to 30 degrees and include the subtropics. So a big chunk of our planet's population resides in the tropical area. That population is going to increase. It is expected to be over 50% by the next decade. That's just 50% within the Tropics of Cancer and Capricorn. So the global population is going to be shifting equatorward. The population center is shifting towards the tropics. So it's already important for the livelihood of people that live in this area. It's going to be even more important because there's going to be even more people living in this area in the future. Also, there's a lot of different events in terms of atmospheric phenomena that occur in the tropics. So you have the floods, you got all the tropical waves, you got tropical cyclones, you got the intertropical convergence zone. Everything that happens in there is very distinct. Okay, so you think that with so many people living in the tropics and so many important phenomena, you think that we understand tropical phenomena pretty well, but we don't. Why don't we? So there's kind of two reasons for this. One is pretty complicated stuff, as we're going to see in today's talk. Also, it goes without saying that colonialism and imperialism are a thing, and a lot of these countries that are in here were victims of imperialism and colonialism. South America, Central America, Africa, the Indonesia region, India. And that had major impacts in terms of the observation systems that we have there. But it's also complicated stuff. We're going to see that today in the talk today. In spite of this complexity and the caveats and the things that happen due to these things, we have had many advances in the last 2 decades. So I'm going to start talking about the many advances that have happened in the last 20 years or so in terms of tropical atmospheric dynamics. Okay, so let's start off with this diagram here that you're seeing here on the screen. So a major feature of the tropics is that if you look at the temperature distribution, so we're looking at the mid-troposphere here at about 500 hectopascals, you'll see that the tropics, so here is 23 degrees north and south, and you'll see immediately that it's all pretty orange and red. So the tropical temperature distribution is pretty homogeneous. It does not change a lot with time. Compare this to the mid-latitudes where you see the polar regions in blue, so these are pretty much colder temperatures, and you see that there's a big change in gradation of changing, especially closer to where we live here in Wisconsin, you see big temperature changes here. Tropics, not so many temperature changes in space. Okay? So pretty homogeneous temperature distribution. Why is that? So imagine that there's a big system of thunderstorms occurring somewhere in the tropics. This system of thunderstorms actually releases a lot of heat and energy from the condensation and freezing that is occurring in these thunderstorms. So there's a lot of energy occurring with these thunderstorms, and this energy actually doesn't stay with these systems, it gets distributed out. So if you imagine this ring here in red being a thunderstorm, and then this shading here being the temperature, you see that the temperature doesn't change where the thunderstorm is, it actually changes throughout the whole environment that surrounds it. So you see that you have this kind of like boom, kind of like explosive development of like a region of warmth. So we can wait for the animation to start over again. So you have the thunderstorm that develops here at 0, and then within an hour you see this ring of high temperature or higher temperature kind of propagate out. So in this animation here, it's actually propagating out at roughly 50 meters per second. So this is roughly the speed of what we call gravity waves, okay? So the process in which the tropics actually gets smooth temperatures is related to this gravity wave that gets emanated by the convection. Now, there's a lot of people that are new to atmospheric sciences and are probably not familiar with gravity waves in the tropics or at all. So this might look familiar to some of you, and in fact, you might be remembering the Tonga eruption from a couple of weeks ago, and a lot of the dynamics that happen in this convective system are actually analogous to that. So there are some major differences. These are not gravity waves here, these are actually land waves. So they propagate much more quickly than the stuff that I showed in the previous slide, but other than that, there's a lot of similarities. You get this kind of like shock wave looking thing, this like big kind of like boom-like explosion, everything goes outward. The big difference is that not the same kind of wave, and they also move a lot faster. These things are moving at incredibly high speeds. The previous stuff is not, but actually works in a similar way in the sense that it kind of forms this like big ring that's moving out of the region. So that's if you're not familiar with that, that's a cool way to think about it. Now, the interesting thing is that this was a singular event. This whole was a big, big event that happened. But the event that I showed in the previous slide, this event here, with the thunderstorm and this whole ring, is actually happening all the time in the tropics. So this is a continuously occurring event. So there's thunderstorms happening everywhere in the tropics all the time, and you're getting rings like this happening all the time, distributing the temperature around and homogenizing it at any point in time. So what happens is that because of the action of these gravity waves, you get the thermodynamic equation here. So this is the horizontally changing temperature derivative. So this is how temperature changes in time. This is actually the adiabatic cooling from vertical motions. And this is the diabatic heating rate. So here, what happens in the tropics a lot of the time is that this gets canceled out, and you just get a balance between the diabatic heating, which is the red stuff that you're seeing in here. So this is the diabatic heating, and the adiabatic cooling that you get from this other term. So these two things are in balance with one another. And this leads to a major balance of the atmospheric sciences that is very prevalent in the tropics, that is known as the weak temperature gradient approximation. All right. So one thing that I mentioned before, temperature gradients are weak. The temperature distribution is very homogeneous in the tropics. However, let's look at this map here. So here, we're looking at the horizontal distribution of column integrated water vapor. So this is about the amount of water that you would have if you just turn it on to liquid water. And you'll see that in the tropics, you actually have very, very large gradients. So there's a lot of contrast. You have regions like here in the maritime continent where the values can be 70 millimeters. And you can have regions like off the coast of Peru where they're like 20. Okay? So that means that the change in water vapor in time and space can actually be very large in spite of temperature being more or less homogeneous. So large water vapor fluctuations, small temperature fluctuations. What does this lead to? So it turns out that these changes in water vapor are really important. Horizontal temperature gradients are weak, but moisture gradients are large. And it turns out that these moisture fluctuations are very important for the organization and occurrence of rainfall. So this is a plot from Rafferton et al., 2004. Column integrated water vapor, you see that as you increase the water vapor, rainfall goes up quasi-exponentially. So very important for the occurrence of rainfall. Okay. Now here's the kicker. I just told you that temperature gradients are weak, but they're not zero. And this is really important for the purpose of this talk today. So temperatures still fluctuate in space and time, even though they're small. And even though they are small, they're actually really important in determining the winds. So we know that there are winds in the tropics. They are in steady state. You got the trade winds, for example. You got the monsoons. So you do have significant changes in wind with time, even though the temperature is small. So why is that, and why is this important? So I was just talking about this because I was just teaching 611 just 20 minutes ago. And we were actually talking about geotropic valleys. So in the mid-latitudes, you get that the predominant balance in the momentum equations is between the pressure gradient force and the Coriolis force. So the two are like at a tug of war, and they're in like a deep tie, essentially, a lot of the time. So they cancel out, and they're approximately in balance. In the tropics, you don't get geotropic balance very often. Instead, you get what we call nonlinear balances. Now, I'll talk in a little bit why they're called nonlinear balances, but if you're not familiar with nonlinear balance, you can think about gradient, wind, cyclotropic, and semi-geotropic balances as being kind of like part of this tree of nonlinear balances. I'm showing gradient wind balance here in the bottom. So you got a low pressure, you got a pressure gradient force, a Coriolis force, and also a centrifugal force, for example. In this case, the centrifugal force is what makes this nonlinear. And of course, because you have balance flow by the thermal wind relation, you have to have a temperature anomaly. So even though temperature gradients are weak, they cannot be zero. You have to have temperature changes because they have to be consistent with the changes in the wind field. So, here's the mathematical expression of nonlinear balance. You got the Laplacian of the geopotential field, the divergence of the Coriolis force, and then you get this Jacobian term here. If this seems pretty complicated for you, the way to think about this is that this is approximately the divergence of the momentum advection. I was just talking about this in 611 and how in the tropics acceleration is about the same order of magnitude as the Coriolis and pressure gradient force. This is the expression of that acceleration in the terms of balances. All right. Now, big important thing here, and this is why I'm showing a picture of a hurricane. So a system that is in exact nonlinear balances should not have any vertical velocity. So here's a hurricane. Hurricane has clouds, has deep thunderstorms. So a hurricane, the wind field is approximately in gradient wind balance. If you're close to the eye, it's actually cyclotropic if you're really strong. But you can't be in exact balance because you have an overturning circulation. So it's always going to be an approximate relation. And that residual, that small departure from that balance, can actually be very important in driving the actual vertical motions, which is what we're going to be seeing today. And this is very analogous for those of you that are more similar with mid-latitude circulations and how departures from geotropic balance are actually very important in the overturning circulations that we see in mid-latitude flow. Okay, so we are going to have a set of guiding principles, and what I'm going to do for the remainder of the talk is tell you what my research and my students, as well as some of my colleagues' research, has said are consequences of these guiding principles. So the first guiding principle is that the weak temperature gradient approximation and the balance that arises governs the thermodynamics often in the tropics. So again, you've got this balance between the diabatic heating and the adiabatic cooling. Okay, so vertical motion cools the atmosphere adiabatically, while the diabatic heating from condensation and radiation actually acts to warm it up or cool it down depending on where you are. The second principle is that moisture is going to be important in tropical thermodynamics. Okay, so we saw in the plot from the Breatherton et al. Paper that as you increase water vapor, rainfall tends to increase. Okay, so this is going to be guiding principle number 2. Number 3 was the one that I just showed you in the previous slide. Nonlinear balance is really important, and non-divergent flows in the tropics tend to be in this nonlinear balance. So this one is going to be, again, showing you the picture again, showing you what nonlinear balance sort of looks like. So what we're going to do, again, in the remainder of this talk, is going to be talking about what are the main consequences of these 3 points and what they mean for tropical weather and climate. So let's go to guiding principle number 1. This one is going to be a direct consequence of weak temperature gradient balance. And this one actually is really actually interesting, especially when you compare it to what happens in the mid-latitude. So for some of you that are not familiar, potential vorticity is incredibly important for understanding how mid-latitude circulations form and evolve in time. In the tropics, you can use potential vorticity to understand how systems in the tropics evolve. If you apply the weak temperature gradient approximation and assume that these systems are in this kind of balance, the PV equation, so potential vorticity, we write it as PV, it actually becomes a vorticity equation. So here's our PV here on the screen, and that's going to be in pressure coordinates, d times the relative vorticity, which is theta, and then this SP here is the static stability. Because wet temperature gradients are weak, this static stability term actually fluctuates very little with time. So when PV changes with time in the tropics, it's because the vorticity is actually changing and not because the static stability is changing. So here's a diagram to the right, and that should help you think about the potential vorticity. So you're looking at the equator here, and these are the theta contours. So this is the potential temperature. In the tropics, these potential temperature contours are approximately pressure contours because they are flat. So a potential temperature surface is also an isobar to a good degree of approximation. And it tells you that these tend to be flat and remain flat with time. And whenever you change the potential vorticity, that's because you're changing the circulation that is enclosed within these two contours that you can choose of your liking. So for example, here, 330, 340, you change the PV here. It's mostly because you're actually increasing or decreasing rotation in this location specifically. So that's consequence number 1. Let's go to consequence number 2. So this one is actually like a really bizarre one, but I'll guide you through it because it actually is pretty interesting. So the weak temperature gradient balance does not allow the vorticity, specifically the vertical component of the relative vorticity, to be flexed vertically. And here the vertical component is really important because vorticity is actually a vector. So you are actually rotating. So if I just started going around in circles like this, I would have an axis of rotation that is pointing upward. And that's the one that theta represents. You can actually have vorticity components in the horizontal direction. But in tropical motions and in weather systems in general, we really do care about this vertical component specifically. Now, the change in time of this component is actually given because of the weak temperature gradient approximation by just 2 components that are written inside of a horizontal divergence. One of them is just the flux, the horizontal flux of absolute vorticity, so you can actually just flux vorticity into a region or out of a region. And then the second term here is actually the vertical flux of the horizontal component of vorticity by the vertical velocity that's balancing the heating. So this is just vertical velocity that's in WTG balance. So every time I see a vertical velocity here, it's going to be WTG, vertical velocity. So it's going to be either driven by convection or by radiation and nothing else, pretty much. So you see here that there's no vertical component going on in here. That's because the weak temperature gradient approximation knocks it out when you do the math. Now, if you don't like the math and want to see the conceptual implication of this, is that if you have 2 isentropic surfaces, so this is like pressure level 1 and pressure level 2, you actually can't flux the vorticity up and down these 2 surfaces. You can only flux it sideways. So you can either concentrate the vorticity, so you can accrete it, like you're seeing here on the left panel, and concentrate it, leading to the red color that you see on the right. But these 2 contours, they work like boundaries. So I'm putting two axes because you can't move the relative vorticity up and down. So the major consequence of this is that when you're seeing a system in the tropics spinning up, is because the vorticity is getting concentrated within a specific level, not because you're moving it up and down. You can only move it horizontally. Okay? That's probably the weirdest of the consequences. So if you're a little confused here, fear not. This is the most complicated one. I will come back to it later on, because it will have important implications later on. Third consequence. So let's think about this third consequence here. So what is consequence number 3? So when we think about divergence, so divergence is just like either things coming in together or just diverging out. Convergence is coming together, divergence is coming out. We are going to find that WTG is going to govern the divergence. So it means that whenever you see divergence in the tropics, it's going to be usually because there's divergence driven by convection, or it's going to be related to radiation. So adiabatic motions are going to be relatively a lot smaller. So here's again your WTG equation. So again, adiabatic expansion, omega is going to be the vertical velocity. I just defined it as 611 here. This is the isobaric vertical velocity. And that's going to balance the diabatic heating, which is the little cube with the dot here. So what this consequence is telling you is that delta, which is going to be the divergence, is just going to be the vertical change in the diabatic heating. So whenever you have a region of heating, you're just going to like have, for example, say a convective cell, all the main heat release is occurring in the mid-troposphere. You're going to have convergence below the region where you're getting the condensation and divergence above it. That is what this thing is essentially telling you. And you're just going to have this as a consequence. So here's the diagram to the right that's telling you this. So here's your Q, so maximum limit levels. You've got your omega going up in this region here. You've got convergence below and divergence aloft. And that's essentially what this consequence is telling you. It's a fairly simple consequence, but we'll see later on what this means. So now we're going to get into like really interesting consequences. These were like more dynamic equations, equal motion consequences. We're now going to go into more thermodynamic consequences. The consequence number 4, and this is based on building evidence from the last 20 years that moisture modes exist. Now, if you don't know what a moisture mode is, it's a type of tropical motion where water vapor specifically plays a leading order role in its dynamics and its thermodynamics. So it's essentially like a tropical wave that is being moved around because moisture is being moved around. So here's the picture again. The column integrated water vapor is going to be the shading. So regions of very high water vapor are in red, regions of low water vapor are in blue. And you see that there's a lot of convection going on here in the regions where the water vapor is high. So if you're in moisture mode, you're essentially a large region of convection that's moving around because the water vapor is kind of shuffling around. So here's from a recent paper just submitted from Maita et al. 2022. Just submitted. We have 3 criteria that if you want to identify a moisture mode in the tropics at any given place and time, here are the 3 criteria. So moisture modes tend to be highly coherent with the water vapor and the precipitation anomalies. So you've got a direct proportionality between rainfall and column integrated water vapor. That's an easy enough consequence to think about. Consequence number 2, the system is in WTG balance. That's kind of like almost expected at this point, but it's stuff that I'm talking to you today because everything that I'm talking to you is essentially weak temperature gradient balance. And then consequence number 3 is that when we look at different thermodynamic quantities, we're going to find that in these types of systems, water vapor is going to be much bigger in amplitude than any other quantity in the thermodynamic equation, and specifically here, the temperature. So we got the LV cubed, so we're talking about here the latent heat in units of energy, has to be much bigger than CPT. So we got the water vapor essentially governs the thermodynamics.
In what place in the weak temperature gradient world of the tropics would that third one never be true, or would not be true?
So this is a good question, and there's 2 possibilities. So if your system is evolving really quickly, so it's propagating really fast, this tends to like not be true. So if you're moving like a speed of like 20 meters per second or more, then temperature tends to be much bigger. And the other one is depending on the vertical structure. So if you have a very high order vertical mode, so like if you oscillate multiple times before you hit the tropopause, that tends to be dominated by temperature a lot more than one that just oscillates once or twice.
And do those kinds of environments tend to find themselves in the wake of other more prominent or more common environments in the tropics, or do we not know that yet?
I think they just all superpose on each other, so
Oh,
like you
okay.
can probably have them because like convection tends to like have either one or second two oscillations, but you can have like a superposition of all of them. So you can have, for example, a moisture mode, you know, and then embedded within the moisture mode, you can have like tidal, you know, gravity waves and other things that are not moisture modes at all. Yeah. Yeah, so these are the three criteria for moisture modes. So like rainfall and moisture are highly correlated with each other. So the system is in WTG balance, and then moisture governs the thermodynamics of the system. So moisture is important in these systems. So consequence number 5, and this is going to be a consequence of the existence of moisture modes. You're going to have a high diversity of tropical weather systems. So like I'm just putting it all colorful because they're going to be super colorful and super different from each other. And I'm not going to talk about the three-dimensional scales, the non-dimensional scales. Like I think that in the interest of time and keeping this more qualitative, we do see that these are certain scales that determine the different modes. But I will tell you that there's just a very few handful of parameters that lead to this great variety of systems. So a few constraints can lead to a great deal of diversity, even though the system is very, very strongly constrained. And one of these constraints is that you have 6 types of motion systems, and all of them are in WTG balance. Okay? So it's not that we're just letting everything rip. Everything has to be abiding to this balance, but even though you still have this balance, you still have 6 types of systems. At least, you can actually have a lot more of them. So let me have a quick sip of water here. We're hour number 2 of me talking, so clearly I need some water here. So here's one type of motion system that we can identify of the 6. So this first type of motion system is called, we are going to refer to as the equatorial moisture mode. When I was putting this presentation together, I kind of wanted to put like a mugshot of all the different systems that exist, but I decided that instead of giving a black one, I'm just going to give a rainbow one. So this is what ended up happening up in here. So the first system is the equatorial moisture mode, and here's a schematic diagram of how we think the system should look like. So as you see on the table here, the equatorial moisture mode has a very large horizontal scale of about 10,000 kilometers and a smaller meridional scale of about 1,000 kilometers. So it's, you know, if you want to think about it in terms of degrees, it's about 10 degrees wide in the meridional direction and 100 degrees wide in the solar direction. So it's planetary scale in the solar direction and not planetary in the meridional direction. It has wind anomalies of about 10 meters per second, precipitation anomalies of about 10 millimeters per day. Now, if you make this schematically, you will just find that this is a very long wave with very strong solar winds, weaker meridional winds, a very, very large moisture signature, and a fairly weak temperature signature, and a cloud, because it's a moisture mode. So it has a lot of moisture and rain, so big clouds. So I guess the obvious example of an equatorial moisture mode is probably the MJO. Actually, my postdoc Victor is going to show probably like in a month or so that there are more equatorial moisture modes besides the MJO. But the easiest example is the MJO. So here's the picture. Yeah.
Sorry, can you go back to the prior slide?
Yeah.
I'm just trying to understand the H and the L represent what?
High and low pressure. So you have like a low pressure near the surface with easterlies and then a high pressure with westerlies.
Okay.
Yeah. And this is, just to make a little bit of sense, more sense of this, these types of systems are geostrophic in the meridional direction, but they're not geostrophic in the zonal direction. So you have strong zonal acceleration, but you're in geostrophic balance in the meridional direction. Yeah, like a Kelvin wave. Yeah, Kelvin wave-like structure. Yeah. Yeah. So the clearest example of this is the MJO. The MJO is probably the most clear example of a potential equatorial moisture mode. For reference, this is Australia down here. This big thing here is the MJO. Here are some twin cyclones. And for good measure, I have done this in the past and people really like it. Let's shove Russia in there, and you can see that Russia sits very nicely in the MJO. So you can, it just tells you that the MJO is actually bigger than Russia, you know, and I usually do this because we usually think of Russia when we think of big things. and the MJ is bigger than Russia, so there you go. There's more than one type of moisture mode. So I just told you about the equatorial moisture mode. They're very, very big, you know, Russia big. So there's a second type of moisture mode that I'm going to refer to as the off-equatorial moisture mode. This one is about 10 degrees in both zonal and meridional directions. Tends to have slightly weaker winds, actually bigger rainfall anomalies. That's a mistake of mine. It's not 3, it's 30 millimeters per day. So they tend to look like cyclonic features. So here's the schematic of them. So they look like a cyclone. They have really big moisture anomalies, fairly weak temperature anomalies, very, very high rainfall rates. And the system is about in gradient wind balance. So the winds tend to, the Coriolis and pressure gradient forces and the centrifugal forces tend to be in balance with each other. Now, if you're like me, and I'm just telling you like, oh, this is the off-equatorial moisture mode, here are all the features, you're immediately going to think about a tropical cyclone because that's the first thing we all think about. Tropical cyclones are actually way too strong and not 3 meters per second, so this is actually more like tropical depressions. The other good example of this is potentially easterly waves in the Pacific, which tend to propagate very slowly. So here's the wind, the low-level winds, and the easterly wave, and here are the anticyclonic features of the easterly wave, and I'm going to throw my student Rosa under a bus right now and tell you that she's going to give a talk about this next month, and she's going to tell you all about the easterly waves of the Pacific in comparison to with those of Africa, and she's going to make your case of whether these are moisture modes or not. So these are the off-equatorial moisture modes. So we've just talked about two types of moisture modes. Okay. So I might run out of time, so in the interest of time, because we don't want to stay here till like 6 p.m., this is not the kind of meeting that you want to be there for 2 hours, I'm going to summarize all the other systems together. So let's look at those. So we also have equatorial mix systems. So a mixed system is exactly like the equatorial moisture mode, except that temperature and moisture are comparable to each other. And the reason why these are bigger is because these tend to move faster. So this goes back to John's earlier question as to how can you have temperature have a bigger role in tropical motion. These tend to move at like 15 meters per second, while the equatorial moisture moves at about 5. So these are considerably faster than the equatorial moisture modes. You got the off-equatorial mixed system, which is a lot like the equatorial moisture mode, like the off-equatorial moisture mode, except that it moves faster. And if you look at the scale analysis of this one here, these guys tend to be bigger than the off-equatorial moisture mode. So these systems are faster and bigger, and otherwise look really similar, except that the temperature and moisture are similar magnitude. Now, an interesting result that we found is that tropical cyclones do show up in the scale analysis as being in WTG balance. And this seems kind of strange because we know that hurricanes have really big temperature anomalies. But if your hurricane is actually moving slowly with time, you actually have so much latent heat release in the thunderstorms of tropical cyclones that the leading order thermodynamic balance is still the diabatic heating and the vertical the adiabatic cooling. So even though they have big temperature anomalies, they still have, the balance still kind of shows up. But it's a little more loose than the other systems because you can actually have rapid intensification and other processes occurring which are going to violate this balance. So we're talking more of like a steady tropical cyclone and more on the weaker end, not the really strong ones. Interestingly, you have a region of overlap between quasi-geotropic motions in WTG. And they come in the form of what I'm going to call moist quasi-geotropic motions. And it seems to be more prevalent in the subtropics. And the thing that I'm thinking about here as a potentially moist quasi-geostrophic system is, for example, a tropical upper tropospheric trough could be one of these systems, or the tropical mean stationary waves. So you do have an overlap region between QG and WTG, which kind of seems oxymoronic because they seem very, very different from each other. But you do see significant overlap between the two. Yeah?
Sorry, for the off-equatorial mix systems, are these something like monsoon depressions or these big gyres that form in the tropics and subtropics?
Like the Evan system? Yeah, absolutely.
Okay.
Those like the ways that are thinking about it. Actually, if you go to Rosa's talk in March, we think that African easterly waves are in this group as well, even though other easterly waves are not. So those two are probably mixed systems. Yeah. So the difference is that they either move fast or they're pretty large in scale. Yeah. Okay, so let's talk about triangles here. So here is the take-home message of this last section. So I'm still talking about the consequences of tropical motions being very diverse. That's one of the big consequences and one of the take-homes that I want you to take out of this talk. So if we assume that moisture modes are an integral part of the spectrum of tropical waves, then I'm going to assume that here. So we're assuming that moisture modes are part of the tropical variability that we see. Then we can assume also that Rossby waves are also part of this variability, and gravity waves, which are the stuff that I showed you at the beginning of the talk. So if you assume that those three things exist, by extension, we kind of have to assume that things that are something in between all of these have to exist as well. So this is a triangle from Adames and Maloney, and this essentially tries to hypothetically connect all the types of systems that exist in the tropics. So everything that I focused on in the last couple of slides are the moisture modes, which are kind of like in this lower right vertex that you're seeing here in the triangle. Here is where moisture governs the thermodynamics. The lower you are in the triangle, the slower evolving the system is. So moisture modes are down here. You kind of have Rossby waves at the slow evolving but temperature governed thermodynamic end of the spectrum. And then you also have gravity waves, because we mentioned right at the beginning of the talk, they're kind of like go kaboom. You know, you got convection, it kind of booms out. They're very fast. Gravity waves are super fast systems. And we have all the fun stuff in between, including the, I'm just going to call these mixed moisture gravity waves, inertial gravity waves, mixed Rossby gravity waves, mixed moisture Rossby waves, and let's put easterly waves there because I don't know where to put them, so let's just put them right there. So these are all the things that happen. So if you're looking at this triangle and thinking it's like, oh my gosh, Angel, what are you showing me here? I'm going to be telling you, it's like, well, this is the diversity of the tropics. It's really beautiful, like a rainbow colors and everything. So what I want you to get out of here is that at the moist end of the spectrum, you only have moisture modes. Only moisture modes exist in this end. But as I showed you earlier in the talk, they can have all sorts of structures. They can come in equatorial long waves of the size of the MJO, Russia-sized moisture modes. And you can have moisture modes that look like tropical depressions. So even though moisture modes are the only game in town, in this end of the spectrum, they also come in all shapes and sizes. Yeah?
So the way this is drawn, it makes me think that, and I see triangles here, is there a similarity between that small corner of this triangle and the larger one in terms of these things sort of scale up, but it's just moisture becomes less important?
So yes, that is absolutely correct. So essentially, all the structures that you see here, so you have so Rossby waves are gyres, gravity waves are kind of like big things that coalesce. As moisture becomes more and more dominant, all these structures become moisture modes. They can have the structure of any of these waves, but they become governed by moisture mode dynamics. So even though they're called moisture modes, they are structurally these other waves. It's just that the moisture becomes so important in the dynamics that the evolution of the moisture determines everything, even though the structure looks like something else. So they are like a group that is very diverse, even though they're like a little tiny group in the corner. Yeah. What?
You need a triangle in the triangle.
So you need, you got a triangle in the triangle, yeah. That's a good way to put it. Getting some inception, thoughts right in there, right? You can zoom and you got another triangle and you zoom in and there's another triangle. Okay. So, all the things that I mentioned earlier, so if you think about the moisture modes, so the MJO, the easterly waves are made, the Eastern Pacific easterly waves are here, maybe African easterly waves are here. The mixed systems are here, so these are the other big systems that I mentioned. And then you have the gravity waves and all the other things that I didn't mention earlier on because they're not in WTD. So these systems here, these are not in WTD, but as you move further to the right of the triangle, you're more and more in WTD. And this gives you this like hypotenuse here that you're seeing on the right. So the more and more you go to the right, you're seeing this tau WTD over tau D. So some of you may have picked up on this and may be wondering what that is. So tau WTD is the time scale that requires you to get to WTD. So there's some time scale that causes the atmosphere to go into WTD balance. Tau D is the time scale in which convection drives the atmosphere. So the longer your convection is lasting, the more likely your system goes into WTG, and hence you're more likely to become a moisture mode. Now, if you're not familiar with this, the TLDR is that if you're slow, you're probably a moisture mode, and if you're fast, you're not. Okay, that's kind of like where it goes. from there.
If I remember the beginning of the talk of the first animation, you had temperature emanating away from convective towers by the action of gravity waves.
Yeah.
So this is kind of interesting that gravity waves set the stage for the weak temperature gradient
Yes.
in the tropics.
Yes.
But they don't really benefit from it because they only show up to regenerate that through these big modes. Is that
Yeah,
right?
yeah. So this is actually really interesting because now I'm talking to you, mid-latitude person. So you know when you have geostropic adjustment, like what happens is like the gravity waves kind of like boom out, but then who benefits are the Rossby waves, not as much the gravity waves. So it's like the analogous, but occurring in the thermodynamics. So the moisture modes are going to get the benefit of the adjustment and not the gravity waves. So it's like kind of like the other side of the coin. Like we're in one, you get the adjustment is in the dynamic equation, the momentum equations, and here the adjustment is in the thermodynamics.
And this is why you're interested in moist PV too.
Yeah, exactly.
And I just have a quick question.
Yeah, go for it.
The tau D is related to the effective Grossman stability?
Yes, that's right.
Inverse of that?
Yeah.
It's the effective.
Yeah,
effective
so
Grossman.
so how quickly it dries. Yeah, that's exactly right.
Okay.
Yeah, I just didn't want to add it because
Yeah, sure.
in the interest of time. Yeah. All right. So kind of starting to wrap things up here a bit, and we're going to get into like some really mind-bending stuff before we wrap it up. So consequence number 7. Remember that we're talking about consequences. It just went like on a 20-minute tangent, but we're still talking about consequences. So one couple of last consequences about WTG is that the horizontal flow in many tropical systems can be decomposed into only 2. So you can actually do a Helmholtz decomposition, and you can actually decompose it into like a velocity potential and a stream function. Through WTG, the velocity potential is in fact in WTG balance, but the stream function is not. The stream function is actually a deviation from WTG balance, and is in fact describing nonlinear balance. So it's actually describing this balance between centrifugal, Coriolis, and pressure gradient forces. So you can actually decompose the horizontal speed into a WTG component, which is purely irrotational, and then a non-divergent component, which is actually rotational, just something rotating with respect to a center of rotation. And you can actually write the thermodynamic equation in terms of this velocity potential up here, is Laplacian specifically. Now, we don't have to look at the math in detail. All you have to know here is that you have a component of the wind that satisfies one balance, and then another component of the wind that satisfies the other balance. So you only need to know about 2 balances in the tropics at any given point in time, and then the 2 balances kind of like cooperate with each other in a way that enhances their evolution. So this is where things get weird for me, and it's probably going to get weird if they're already not weird for anybody else. So under WTG balance, the primitive equations actually collapse to 2. And this is actually something that I just revised and submitted, and this is just freshly off from my iPad to the manuscript and now to AMS, I guess, is the way to think about it. So you only get 2 equations. So earlier on in the talk, I mentioned the vorticity equation. So that's the one that actually comes out. And that vorticity equation describes the evolution of nonlinear balance. So again, remember the hurricane that we saw earlier. Number 2 is that you get a divergence equation that describes the diabatic heating. So it describes the state of WTG that you see in the tropics. So in order to kind of like think about this actually in a way that actually makes kind of sense, I put all the primitive equations on the left. So you got the momentum equations, hydrostatic balance, mass continuity, thermodynamic, ideal gas law, and the moisture budget. And all these equations collapse into 2. You'll only get a vorticity equation, which describes, see here, so it describes the stream function, and then you got the divergence equation, which describes the velocity potential. So you only get 2 equations, one for the rotation and one for the divergence. And this is actually really surprising because I really thought that the moisture budget was going to make it to the end, and it actually did it. It actually kind of like combines with the continuity thermodynamic and momentum equations into the divergence equation. So then you get this set of equations here. So, and here I'm going to end, this is going to be my last slide before I go on to the conclusions. I had another equation, but I'm not going to like show it here. So I remember that I showed you earlier the vorticity equation, and I showed you that the vorticity equation is just a horizontal divergence. You can't actually, oops, I actually skipped the slide because I don't know how to work this remote. So I showed you that you have a horizontal divergence here, and you have this term, you got only 2 terms and a divergence. And I told you that you actually can't move the vorticity up and down pressure levels. You can only have them within pressure levels itself. the divergence equation actually looks pretty similar, except that you have a flux of divergence and then like a vertical advection of the momentum. And the only difference that actually differentiates these two equations is the sigma term here. And this actually is the deviation from nonlinear balance. So remember that rotary thing that I showed you earlier? Any small deviation in that is going to cause a divergence tendency. So remember when I mentioned earlier the hurricane? Like the hurricane is not exactly in nonlinear balance. We have a small deviation, and that small deviation is driving the evolution of the divergent circulation, which is the overturning that's driving the convection within the system. So here are the consequences of that, and I'll like open it up because we're kind of starting to get late here. So there's a bunch of consequences in here relevant to tropical weather and climate. The first is that these equations are closed. Everything that you see up here can be written either in terms of a string function or velocity potential. So you can actually like create a tropical weather model with just two equations and see what happens. I don't know how it would look like because I haven't done it, but in theory it seems like it's possible. Number two, the equations exhibit a high degree of symmetry. If you look at these two, they're very similar. There's a flux term here, a flux term here, some kind of vertical velocity related term with shear, and another vertical velocity term with shear. And then only the sigma term actually really differentiates the equations from each other. They're very symmetric. Number three, they actually don't require any explicit information about convection or radiation. And this is where things get really weird, because we're always talking about the importance of radiation and convection. But when we collapse the equations, all this information about convection and radiation kind of gets shoved into this equation here and sort of disappears. So you can actually run the model without actually explicitly running radiation and convection, because all you need is actually the initial conditions. So yeah, super weird, still thinking about it.
Wait, but isn't the omega W the convection and radiation? That's a
Yeah, it is.
TG vertical velocity.
But you don't, it's in there, so you don't have to like run a radiative transfer scheme or a convective parameterization. You just need to run that equation here.
But how do you get your omega?
Initial conditions.
Okay.
Yep. So super weird. So you only need the initial conditions, and you don't need other information about convection or radiation other than this equation here. This is
But
very strange.
The omega is going to evolve over time, right?
Yes, it will evolve over time because it has to follow mass continuity with the divergence.
Oh, I see. Okay.
Yeah.
The divergence is changing the omega.
Yeah, the divergence is changing the omega. Yeah, exactly. Yeah,
Then
yeah,
you
yeah.
can go back to the Vorticity
Yeah.
equation and keep on.
Yeah. So the two equations that I'm going to show in the last slide here, these two equations are actually interacting with each other. So that the vorticity is changing the omega is changing the vorticity, and then you kind of go on the loop with each other.
So can you combine those two into
Yeah.
one?
I haven't been able to. This is as yeah, this is as good as I've gotten it, but maybe, I don't know. So this is a consequence that's probably more related to climate, but when you globally average these two equations, they have to go to zero. You can't have globally averaged divergence, you can't have globally averaged vorticity, and because most of these two equations are within a divergence operator, when you average globally, the divergences disappear. So you actually get no tendencies. And this sigma here actually also goes away because you can also write it in terms of the divergence. So globally average, the two equations just completely disappear. And the weird thing here is that points 1 to 5 really severely constrain the large-scale circulation, because then you just have two variables, and then the two variables are kind of constantly going on a loop with each other. And because they have to globally average to zero, essentially, for example, if you have like a hurricane forming, it's essentially grabbing all the vorticity from its surrounding, but the global integral has to remain the same, so you're kind of like just grabbing vorticity, not kind of creating it on its own. So this is a big constraint as to how the global circulation has to behave. So I'm going to skip this in the interest of time. Oops. So I'm going to check here. I'm going to end it with me on the floor, of course. So here's the big conclusions, in case this was weird and didn't make a lot of sense at the end. So horizontal temperature gradients are weak. Moisture gradients are large. There's a big diversity of tropical weather systems in WTG balance, 6 of them. Under WTG balance, the equation is reduced to 2. So everything kind of gets combined into a single equation. And all the information about moisture, radiation, all these things are kind of like implied in them, so they don't go away, they're still there. But they kind of like all kind of combine into one equation, which is really strange. And then the consequences of these have yet to be fully explored, and this is just me honestly telling you that like I found it, I wrote it, I submitted it, and I still don't know what's going on. So, and I don't know if the reviewers are going to figure it out either. So, so thanks for your time. Here's, I'll open up for questions. Here's the citations for the two main papers. QR codes for those of you that want to just take a picture and see, here's the URL for the manuscript, the preprint, and then the second paper is already published, so that came out last year. So if you're interested and want to give it a read and have a chat about it, I'm more than happy to have a chat because I'd be super down to like trying to think about of this a little bit more. So thank you, and yeah, if you have any questions, just let me know.